You might be noticing by now, if you look at this board here, that even though we're several videos into this lecture series, we haven't actually solved a problem yet. And the answer is it's going to take some time, because the method of partial fractions has a lot of requisite knowledge. A lot of this stuff is things you should know before, but you probably don't. So we're going to go through this methodology so that we can eventually get to the calculus. Now, with that being said, if I have a polynomial, two polynomials, one on top, one on bottom, and you can factor that bottom polynomial into a sequence of other polynomials, then we can perform this conversion. We can say, all right, I can write these as actually a bunch of separate rational expressions. So I can take each of those factors and set them up as their own. Each of those fractions, or each of those factors, is its own fraction with some sort of unknown polynomial on the top, and then this little polynomial out to the side from the long division. I can always do that. The key, though, is you need to follow this, what I'm going to say is a 5-step process. And the first one is that if the degree on top equals the degree on bottom, or is actually greater on top, then we need to use that long division that we just talked about to get this q of x. And then what we'll end up with is a q of x and then a separate polynomial, and then that separate polynomial is what we'll actually do the decomposition on. So we would end up doing this and then a separate one. So you'd actually have something like this, and then we would do the partial fraction decomposition. And the reason why I say that is because if the degree is actually less on top, this is 0. We actually don't have a long division term. So it's kind of a 2-step process there. But anyway, that doesn't always come up, but it does sometimes. The next thing you want to do is just factor that polynomial into a sequence. Factor it as best you can. Just, factor it as cleverly as you can into all these different components. That part's pretty easy. The next part is a little bit tricky. And it's not really tricky once we get to doing it, but the general form is kind of nasty to wrap your head around if you haven't done it. And that's that. What we're going to do is, if I have some sort of linear terms, think like 2x plus 3, or x minus 4, something like that. That's a linear term, right? The degree of x is 1, and it might have a coefficient on the x, and it might have an additional shift or offset term. But that factor might not be just 2x plus 3. It might be 2x plus 3 quantity squared, 2x plus 3 to the 5th, something like that, right? That might be the way it's factored out. So what we do is that power on the outside, again, if it was 2x plus 3 to the 5th, that power there is what's called the multiplicity. That's called the multiplicity of that factor. And don't worry about what multiplicity means at this point. There's a lot of really interesting mathematics about the multiplicity of factors, but all that's really telling you is that for each of those potential degrees up to the total multiplicity, we actually have a separate fraction. So again, if the factor was 2x plus 3 to the 5th, we'd have to do a separate fraction for 2x plus 3, a separate fraction for plus 2x plus 3 squared, and a separate fraction for 2x plus 3 up to the 5th. Obviously the 3rd and the 4th would be there too. And the key for those is that the term on top is just some coefficient. And we don't know what those numbers are. We're going to solve for them. So you just sort of set this up, just sort of write it out, and we'll get there when we get there. Now the next piece is what happens if you have what's called a quadratic factor. A quadratic factor means there was no way to factor it away from a degree 2 term. Think like x squared plus 4, right? You can't factor x squared plus 4 over the real numbers. And we're not dealing with like complex number stuff here. Though, interestingly enough, if you were able to do that, there is calculus that makes that really interesting and makes it all work the way you would expect. Super cool stuff. But anyway, if you had like x squared plus 4, you can't reduce that. So that's what's called a quadratic factor. So if we had something like, think like, I don't know, x squared. I'm trying to think what this would be. Sometimes this is more factorable than you think, but anyway. So think x squared plus 4. We're not going to worry about that middle term. X squared plus 4, let's say to the 3rd power. what you would do is you would say, all right, I need x squared plus 4, squared plus 4 squared, all the way to x squared plus 4 to the third power. But the key here, and this is the real trick, is that now the term on top isn't just some number, it's actually a linear term. So if the bottom factor is quadratic, the thing on top is bx plus c. So this is b1x plus c1, b2x plus c2. But notice that the term on top doesn't change the format. Like, it's not squared and cubed and whatnot. It's the same term every time. Well, it's not the same exact term. It's b1 versus b2. Those are separate, distinct numbers. But if you have a linear term, you subtract 1 degree. Well, if it's a linear term, 1 degree less is just some constant. If it's a quadratic term, 1 degree less is a linear term. So what you actually find is if you have like a cubic term, and we're not going to deal with that here, but if you had a cubic term, you would have a quadratic term on top, and that's how this method works, and is one of the reasons that we require that the degree on top here has to be less than that there. Otherwise, things just go really, really squirrely. It's not really workable. The final piece is that we need to use various solver methods, and we don't have enough board space to cover that for this one. But what I wanted to do is talk a little bit about the problem that we originally motivated that with, which is this 1 over x squared minus 5x plus 6. So let's talk about the steps. The first step is to say, all right, is the degree on top greater than or equal to the degree on bottom? No, it's not, because that's degree 0, this is degree 2. So there's no need to do that long division, thank goodness. The second one is we just have to factor it. Okay, when I factor it, I get 2 linear terms, x minus 2 and x minus 3. Now if I go to this piece, what I do is I say, okay, this is actually this, so these linear terms are here. So then I can represent that as a over x minus 2 and b over x minus 3. Don't get wrapped up in the fact that these say a's and these say b's. They're all just letters. So typically what ends up happening is that when you have a small amount of terms, you don't use A1s and B1s. You just use the available letters. So if I end up with like 8, and you won't end up with 8 for what we're going to do, but if you ended up with like 8 fractions, you would just use A and B and C, D, E, blah, 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 down the line. Only when you get really, really, really large stuff do you really need this, but you have to write it that way when you're writing general forms. So anyway, we write that, we write here. Now in the fourth case, we actually don't have any quadratic factors because none of these factors were quadratic, so we don't need to, but we'll get to those as we go along. And then in the later videos, we'll talk about how to solve for what A and B are. Now, if you fiddle this a little bit, you'd actually find this is 1 and this is -1, and this is -1 and this is +1, and it's pretty easy to solve and figure those out. But the idea here is we're trying to figure out ways to separate these into separate fractions, because separate fractions make for easier integration.